Hello everyone, this is part 3 video on past year NEET questions from the topic solid state. Now those who are looking at this probably can take a look at the other two parts also, so that if there are any repeated questions means you will be able to follow the the approach easily. We'll start with the first question. This is a question that has come in the year 2008. With which one of the following elements silicon should be doped so as to give a p-type semiconductor? Now if you look at a silicon, right, so what will be there in a silicon crystal structure? Each silicon will be bonded to 4 more silicon atoms. So we require a p-type semiconductor. P-type semiconductor means what? So p-type will have more number of holes. The hole concentration will be more. So normal semiconductor, the number of holes will be equal to number of electrons. Why? Because if an electron comes out of its place, it is going to give an electron that is free and so the number of holes will be equal to number of electrons in a normal semiconductor. But if you are doping them means, say for example, if you are doping them with 13th group element like boron or gallium, what happens if one of the doping will be done by using a very small concentration. These boron atoms will go and occupy the lattice sites. So boron has got only 3 valence electrons. So on 3 sides it will satisfy the valency, but the 4th side it cannot satisfy the valency. This is the hole. So for getting the p-type doping, right, p-type doping will be giving us more number of holes than the electrons, and that is possible when we have the silicon doped with a 13th group element like boron or gallium. So if you use 15th group elements, so what is the answer for this question? The answer for this question is option B. If you use 15th group elements like say for example phosphorus or arsenic, then what happens? If an arsenic is occupying the site of silicon, on 4 sides it will form the 4 bonds, but it will be having one more extra electron. Why? Because arsenic, the number of valence electrons is 5. So thereby the doping with 15th group elements, right, will have extra electrons. That's why this is called as what? N-type doping. So 13 group elements, if we are mixing a small amount or trace amount of the 13 group elements with silicon, we will get the p-type semiconductors. If we mix a small amount of 15th group elements, we will get the n-type semiconductor. So this is another question that has come in the year 2008. This is based upon the radius relation. If A stands for the edge length of the cubic systems, they are giving the order simple cubic, body centered and face centered. Then the ratio of the radii of spheres in these systems will be respectively. Means we have to find what is the ratio of the radius of these spheres. See, if you look at a simple cubic, right, along a edge length, we will see that 2 corner atoms will be touching. Means the value of A will be equal to 2R, which means R is equal to what? A by 2. If you look at an body centered, along the body diagonal, so along the body diagonal the atoms at the corners and body center atom, they will be touching. Means the total this length will be 4R. So 4R will be equal to, what is the body diagonal length? Root 3 times of A. Means R will be equal to root 3 A by 4. That is for the body centered. Face centered means along the face center the atoms will be touching, the corner atom and face center atom. Means the total length is 4R. So here 4R will be equal to, the face diagonal value is root 2A. Means R will be equal to root 2A by 4, which is A by 2 root 2. If we cancel the root 2 means. So they are asking us what is the ratio of the radii of these spheres in these systems. So what will be the ratio of these radii values? First simple cubic, right, R is what? A by 2. BCC, R is what? Root 3 A by 4. FCC, R is what? A by 2 root 2. So what is the correct answer for this? Option C is the correct answer. So sometimes even in the other past year paper discussion, we have seen that we are getting questions on the radius relation straight on the numerical application. Like they would be giving us what is the edge length of the BCC type metal, then they will ask us what is the radius of the metal atoms, or they will ask us the radius of the metal atoms if it is forming FCC, like that. Okay. Let's move on to the next question. This is another straight standard question. The fraction of total volume occupied by atoms present in simple cubic. So means basically we have to find what the packing fraction value. Packing fraction in case of simple cubic. Now what is the packing fraction formula for any type of cubic cell? Z into 4 by 3 pi r cube divided by a cube. That is the number of atoms per unit cell. Simple cubic means what is Z value? Z is equal to 1. And this formula will be simplified 4 by 3 pi r cube by a cube. This will be simplified when we look at the relation between the r value and a value. Simple cubic means what? If you look at edge means both the atoms will be touching each other. This is one atom at the corner, another atom at the corner. Means 2r is equal to a. Means in place of r, what you can substitute? In place of r, we can put it as a by 2. Or in place of a, we can use 2r. So in this formula, right? So 4 by 3 pi r cube divided by, look at this, in place of a, we will substitute 2r. 2r the whole cube means 4 by 3 pi r cube divided by 8 r cube. So r cube is cancelled, 4 1s are, 4 2s are. Means how much it is going to come? Pi by 6. So what is the packing fraction value? It will be pi by 6. If you simplify in terms of decimal, it will be coming as 0.52. Clear? This is a question that has come in the year 2007. If NaCl is doped with 10 to the power of minus 4 mole percentage. So if NaCl is doped with 10 to the power of minus 4 mole percentage of strontium chloride, the concentration of cation vacancies will be. See why the cation vacancies will come? Because the strontium, right, is a divalent ion. It will occupy the, so in terms of charge balance, right, what it does, it will occupy the, the sites of 2. The equivalent of 2 Na plus ions will be what? Just one strontium ion. Means whatever the concentration of strontium ions, right, because in place of 2 cations, we are bringing only 1 cation. Means the concentration of strontium and the one where the site is vacant, that is what we will call as the cation vacancy. Concentration of strontium ions will be equal to what? It will be equal to the concentration of cation vacancies. Clear why it is coming? Because each strontium will take equivalent of 2 cations. But it's like what? In place of 2 cations, we are bringing only 1 cation. Means whatever is the cation vacancy, the other place is going to be like vacant. Overall charge wise it is balanced. The other place is like what? Vacant. So the number of vacant sites will be equal to what? Number of strontium 2 plus ions we are bringing. Clear? So if in case, we'll just give you another example so that it will be very clear. So if I say for example, this is not a thing that will happen or anything. We are just taking an hypothetical example. If say for example an aluminum 3 plus is replacing Na plus ions. Means what is going to happen? In place of 3 Na plus ions, we will get only 1 aluminum. Charge balance. Means 1 cation site will be occupied by the aluminum ion. The other 2 cation sites are going to be what? Vacant. So here what we see, the concentration of cation sites will be equal to 2 times the concentration of aluminum. So whatever the number of aluminum ions coming in, the cation sites generated will be twice of that. Like that it will come. Okay. So here what happens? The concentration of strontium 2 plus means strontium 2 plus is occupying one of the Na plus ion position. But the other Na plus it will not occupy. And charge wise it is balanced because each strontium can balance the charge of 2 sodium plus. So this is the conclusion. Concentration of strontium 2 plus is equal to what? Concentration of cation vacancies. But what is this concentration of strontium 2 plus means? They are giving us in terms of what? Mole percentage. Mole percentage means what? What is mole percentage? This is basically the number of the strontium ions by Avogadro number into 100. That is given as what? 10 power minus 4. Now from here we are looking at what? The number of strontium ions concentration. That is nothing but the concentration of the cation vacancies. So what is it going to be? The concentration of cation vacancies is going to be equal to what? So we will just rearrange them. When we rearrange them, what is going to happen? The 100 will go to the denominator, Avogadro number will go to the numerator. So what is going to come for us? 10 power minus 4 divided by 100 into Avogadro number. So what is it? It will be, I mean, you can see here 10 power minus 4 divided by 100. This will be totally 10 power minus 6. 10 power minus 6 in 10 power 23 is what? 10 power 17. So 6.02 into 10 power 17. So here what are we doing? Basically we are looking at what is the relation between the cation sites and the concentration of the strontium ions, and just going on with the conversion. So this is an important term whenever we hear this mole percentage. Mole percentage means what? The quantity of that particular the number of atoms or ions, whatever it is, divided by Avogadro number into 100. That is what we call as the mole percentage. Per mole how much it is there. That's what is the mole percentage. Okay. Look at the next question. This is another theoretical question. This has come in the year 2006. The appearance of color in solid alkali metal halides is generally due to, means in solid metal alkalis, right? I mean, this will show what we call as the metal excess defect. So if you have a metal alkali, generally the sodium chloride or these alkali metal halides, if the vapors of these metal are made to settle above the surface, right, what they will do is they will attract the ions from inside the lattice, and here the Na will release electron. The electron will go and occupy the site of this chloride. Previously wherever the chloride was there, the electron will go and occupy the site. These anion sites, right, which are occupied by the unpaired electrons, we will call them as F centers. So it's basically the short form for Farben center. Okay, it's a German word, and basically the word comes from the fact that these electrons which are present there, they will keep getting excited, and that will result in characteristic color. That's why they are called as what? Colored centers. So the appearance of color is because of what? It is because of the F centers or Farben centers. Let's move to the next question. This is a question again that has come in the year 2006. Cesium bromide crystallizes in a BCC lattice. So how it will be? Cesium will be at the body center, and the bromide ions will be at the corners. The total number of cesium ions per unit cell will be equal to 1. Total number of bromine ions also will be equal to what? 1. The unit cell length is 436.6 picometer. Atomic mass of cesium is 133. Atomic mass of bromine is what? 80. The Avogadro number, they are saying take it as 6.02 in 10 power 23. So we have to find what is the density of the cesium bromide. So density of ionic substances, right, we'll have a similar formula like that of the density of the metals, but there will be small difference. So look at the formula. Density of normally what we say, density D of a metallic lattice will be equal to what? It will be equal to Z into M by, we'll have the same formula. So V or A cube into Avogadro number. So here Z will represent what? The number of atoms in unit cell, and M represents the molar mass of the element. Now here also we'll have a similar formula, but there will be a difference in terms of what these words will mean. Z here will represent the total number of ions, the total number of ionic units per unit cell, which means here if you look at it, right, there will be one cesium and one bromine, means in a unit cell there will be one cesium bromide unit. So Z will be equal to what? 1. And molar mass here will be equal to what? The molar mass of cesium bromide, which is 133 plus 80, it will be equal to what? 213. And V will be volume, and N is the Avogadro number. Volume will be equal to what? Same, A cube, because it is after all cubic cell. So if we substitute, right, what we are going to get, and again the units part. So here A is what? 436.6 picometer. So 1 picometer, will convert this into centimeter. So if molar mass is in gram, and we will take the value of the edge length in centimeters, then the density is going to be coming in gram per centimeter cube. So we'll substitute the values. Z, the number of cesium bromide units in a unit cell is equal to what? 1. What is the molar mass of cesium bromide? 213. Divide by, so we are converting the edge length into centimeters. So 436.6 picometer, right, means what? 436.6 into 10 power minus 10 whole cube will come, because volume is what? A cube, into Avogadro number. Okay, so Avogadro number, see, if they are giving 6.02, right, I mean we can take it as 6.02 also. Otherwise we can take it as 6.023, the normal value. The thing is, we may get some small difference in terms of the final, just some decimal place here and there we may have to change. But usually for the questions that we get, right, if you quickly take a look at these options, means what we see, the options are quite distant. It's not like we have 4.25, 4.28, like that we are not getting the answers. What are the options? 4.25, other option is 42.5, then 0.425, then another option is 8.25. They are quite distant. So if you simplify this, right, what is the approximate value we are going to get? 4.25. Unit is going to be what? Because the molar mass is taken in grams and the edge length is taken in centimeters, the density will be coming in what units? It will be coming in the units of gram per centimeter cube. So what is the approximate value? 4.25 gram per centimeter cube. I think we would have been talking about it whenever we have these density problems, right? The density problems will involve these numerical calculation part. Okay, let's go to the next question. This is a question that has come in the year 2005. This is a fundamental question related to the FCC. In a face-centered cubic lattice, a unit cell is shared equally by how many unit cells? See, we have heard about a corner lattice point is shared by how many unit cells? Face-centered is shared by how many unit cells? Body-centered is shared by how many unit cells? Edge-centered is shared by how many unit cells? But this is a different question. What they are asking, a unit cell itself is shared by how many unit cells? So if you look at an FCC, right, so this is how we can see the FCC. So if you focus on one FCC unit cell, right, I am marking each of these sides. So like side 1 we have sharing. This unit cell is shared on the side 1 also. It's shared on side 2, shared on side 3, it is shared on side 4, and it is shared with the above side 5 and side 6. Totally how many faces are there? The number of faces, right? What is the number of faces? Number of faces is equal to what? 6. And on each side this unit cell is shared. Means what? In a FCC, the unit cell itself will be shared with how many unit cells? It will be shared with 6 unit cells. So in a FCC, unit cell itself, right, will be shared with how many unit cells? It will be shared with 6 unit cells. Let's move on to the next question. This is a question that is based on finding of the molecular formula. So compound is formed by the elements X and Y. X and Y are forming the compound. The atoms of X are at the corners. So where are the atoms of X? Atoms are X are at the corners. Means 8 corners will be there. Each corner, what is the contribution? 1 by 8. Okay. And the atoms of Y are at the face centers. How many face centers are there? There will be 6 face centers. Each face center, what is the contribution? 1 by 2 for the unit cell, because face center will be shared by 2 unit cells. Then they are asking what is the formula of the compound. So what we will do, we will first calculate what is the number of X atoms in the unit cell. What is it? X is occupying the corners. Means 8 corners are there. Contribution of corner to the unit cell will be what? 1 by 8. 8 into 1 by 8 is equal to 1. Then Y atoms are occupying the face centers. There will be 6 face centers. Each face center contribution is what? Half. Then the total number of Y atoms will be equal to what? 3. We have to find the formula of the substance. So if you look at the simple ratio, right, what is simple ratio of X and Y? 1:3. So what will be the formula? XY3. Option A is the correct answer. Clear? Let's go to the next question. This is a little bit interesting question, and probably this word itself, right, only one of the previous years they have coined this word. Look at this, the pinometric density. What is this pinometric density? Here the K is silent. What is this pinometric density? It is what we see as an approximation of the real density. Okay, so pinometric density of the sodium chloride crystal is what? 2.165 into 10 power 3 kg per meter cube. What is the pinometric density? 2.165 into 10 power 3 kg per meter cube. Okay, while the X-ray density is 2.178 in 10 power 3. What is this X-ray density? So when you pass X-rays through the particular crystal, what happens is the X-rays will pass through the voids. Means the volume that is calculated, right, will be almost seen as the real volume occupied by the atoms. Means that way the X-ray method, right, is not calculating what is the volume occupied by the vacant sites or the unoccupied sites. So as a result, what we will be getting is there will be a difference between the Pinometric density and the X-ray density, because the X-ray density will not take into consideration the volume of the unoccupied sites. As a result of it, right, we will see that the densities will be different. Generally the X-ray density will be what? Higher. Generally X-ray density will be higher. Now what we need to find is, we need to find the fraction of unoccupied sites in sodium chloride crystal. We have to find what is the fraction of unoccupied sites. So if you look at it, let's say we have the total molar mass of sodium chloride is what? M. Then molar volume. What do you mean molar volume? The volume for 1 mole of substance will be equal to what? Mass by density, right? What is the molar volume? Let's say the actual molar volume is what? Mass by, we have to use the Pinometric density, which is 2.165 into 10 power 3, which is what? M into 10 power minus 3 by 2.165. And what is the V dash? V dash is the volume that is considered by removing the unoccupied sites. That will come from the X-ray density calculation. It will be equal to what? M by 2.178 into 10 power 3, means what is it? M into 10 power minus 3 by 2.178. Now the volume of the unoccupied sites will be given by what? The volume of the unoccupied sites will be given by V minus V dash. We can see V will be higher here. V will be higher. The volume of the unoccupied sites is given by what? V minus V dash. So V minus V dash divided by V. What is it? V minus V dash divided by V, right? It is going to give us what? It is going to give us what is the fraction of unoccupied sites. Means what we have to do? V minus V dash means what? V minus V dash means this value minus this value. So V minus V dash will be equal to what? M into 10 power minus 3 1 by 2.165 minus 2 pi 178. That is the V minus V dash. Okay, so V minus V dash divided by V is going to give us what is the fraction of the unoccupied sites. So if you look at this, right, the fraction of unoccupied sites, I'll just rub this off so that we'll be able to see this part clearly. So the fraction of unoccupied sites will be equal to what? It will be equal to V minus V dash by V. So V minus V dash, if you simplify it, right, this will be coming as what? If you take an LCM and simplify it, it will be coming as 0.013 M into 10 power minus 3 divided by 2.165 into 2.178. This is V minus V dash. So V minus V dash by V. What is V? This one, right? M by 2.165 in 10 power minus 3. So here we can see M 10 power minus 3 will be cancelled, and this also will be cancelled. So what we have is 0.013 divided by 2.178. That will be approximately, if you simplify, right, it will be 5.96 in 10 power minus 3. So here also we can see the options are not quite close by. So they are all different in terms of the powers of 10. So option A is what? 5.96. Option B is what? 5.96 in 10 power minus 2. Option C is what? 5.96 in 10 power minus 1. Option D is what? 5.96 in 10 power minus 3. So approximately this one, right? What is it? 0.013 by 2.178. This will be coming approximately to 5.96 into 10 power minus 3. So this is how we will find what is the fraction of unoccupied sites. So always, Pinometric density means what? It is like the real density. It just gives what is the mass divided by the total volume as per the unit cell calculation. X-ray density will consider only the volume that is occupied by the actual sodium ions and chloride ions. So if there are unoccupied sites, means X-ray density will be coming as what? It will be coming as the value of X-ray density will be coming as higher. Why? Because it will not count that particular volume. So that's why the volume, in case of molar volume, will be higher. X-ray density based volume will be what? Lesser, because there is only considering the volume that is occupied by the sodium or chloride ions. So the difference between them is what? The unoccupied sites, and we are looking at the fraction of unoccupied sites. Clear? So what is the answer for this one? It is 5.96 in 10 power minus 3. So this is the question that has come in the year 2001. So this is a fundamental question based on the HCP structure. When zinc converts from melted state or molten state to its solid state, it has HCP structure, hexagonal close packing. So both HCP and FCC, right, they are considered as what? They are considered as the close packing arrangement in 3D. Both of them will have the same packing fraction or packing efficiency. The question is what? Then find the number of nearest atoms. So for every zinc, the number of nearest atoms is also what we call as the coordination number. So what do you call it as? Coordination numbers. In a metallic crystal, the number of nearest atoms is called as what? Coordination number. In an ionic crystal means coordination number is what? The number of nearest oppositely charged ions. That is what we call as the coordination number. So if you look at an HCP, right, this is how we will form the HCP. So we will have a layer of type A where you have a central atom surrounded by 6 atoms. That's why the hexagonal. Then B will have 3 atoms forming a triangle. Then another layer of A, then B. So this AB type. So what is the type of arrangement of these hexagonal? So each layer will be what? A 2-dimensional hexagonal layers. So we'll have a 2-dimensional hexagonal layers and we arrange them in what manner? AB type of manner. Okay. If it is ABC, then we will get the FCC type. So we'll have ABC and ABC type, right? We will be getting what? FCC type of arrangement. But both of them will have the same packing efficiency. So if you observe this, consider an atom, zinc atom, the one that is marked red. It is surrounded by 1, 2, 3, 4, 5, 6 atoms in the layer. 7, 8, 9, 3 above layer. 10, 11, 12, 3 below the layer. Totally, what is the nearest atom surrounding a zinc? It will be what? 12. And that is what we call as the coordination number. So coordination number in a metallic HCP structure is what? 12. So this is about the part 3 video, and we will see in the part 4.